No pause, but there is still a .c tomorrow.
You guys should all go to. There's a special dinner.
Okay. No. Okay. So what we're doing now is we're going back and looking at differential equations. This is a great application of contraction maps and fixed point theorems. So we're going to take the special case where a function depends only on one variable. And how many of you have taken advanced physics classes? So most of the key partial differential equations you see, the reason we call them partial differential equations is because they have many variables of interest. If you look at Maxwell's equations, lots of stuff of interest going on. This is a very special case. So we will assume y prime is f of t and y for some nice f. And of course, the question is, what is the nicest, or in some sense, I guess, what is the least nice f we can take and still have the argument work? And the goal is, when do we have something like this where we can solve? So for example, let's say I have y prime equals y. That's a very nice function. F of ty is just y. Any thoughts on the answer? I'm sorry? It's really y prime of t is y of t. So what would be the answer in this case? E to the t. Anything else? I have to ask C? Constant. I'd go with A because it's not an additive constant. But why is A e to the t a solution? Well, if I solve this, if I multiply by 5 or 7 or 13, it's still a solution. Can I change t to 3t? No, because then when I differentiate, I'll get a factor of 3 coming out. Okay, this isn't too bad to solve. What about y double prime of t equals y of t? So now we have e to the negative. So we would have a e to the t plus b e to the minus t. And in general, every time you have another derivative, you have another arbitrary condition. So you have the number of free parameters you have is going to essentially equal the number of derivatives. And so here I have one derivative, I have one free parameter once I fix it. Frequently you fix either the value at the origin or you fix the derivative at the origin, something like that. What would f be in this case? So here f of ty is just y. What would f of ty be in this case? It would just be what would f of ty be in this case? Is there any f that I can choose for this case?
Third derivative.
I'm sorry?
Third derivative.
Not third derivative. Is this equation in this form?
No, couldn't you take the derivative of both sides with respect to t to get into that form?
And then I have y triple prime equals y prime.
Okay.
And this equation does not fit into this form. This is a first order differential equation. Not every system of differential equations, not every differential equation we want to solve fits into this form. There's a lot of things that do. And so what we're saying is the first derivative changes in a very nice way depending on where you are. If you've seen Professor Adams' lecture on zombies, some of the stuff in terms of the flight path zombies take towards humans as they try to devour them, just expressing your derivative in terms of where things are and stuff like that, that might be a really good application of something like this. Okay? But it's important to note that this does not cover all classes of differential equations. If I want to prove that a second order differential equation has a solution, this method that I'm going to show you is not going to work. Okay. How many of you know all the different debates Professors Adams and Garrity have? Which one is the one that's relevant for us here? The integral versus the derivative. So if we have y prime of t equals f of ty, this is screaming at you to do something, right? What is this screaming at you to do? Integrate both sides with respect to t. So the integral y prime of t dt equals the integral of f of ty dt. And let's say we integrate both sides from 0 to maybe some number tau. Well, what would this become? This would become just y of tau minus y of 0 is the integral from 0 to tau of f of t y of t dt. And so now we can begin to get the sense of a type of equations we might want to solve. Frequently, without loss of generality, often assume y of 0 equals 0. Is it a big deal to assume y of 0 equals 0? I'm just translating the function y. Is that going to affect greatly y prime of t? No, it's not going to affect y prime of t. Now, if I replace y with y minus 5, I can fix that by just changing my function f in a very nice way. So, simple change to f, right? This is a very common theme in mathematics, is you often want to reduce things to simple cases. And so without loss of generality, we might as well assume y of 0 is 0. And now we have this interesting thing. Y of t is the integral from 0 to tau of f of t, y of t. So we're trying to find what function can we put on both sides of this equation and make this true. And this is where we're going to use the contraction map. This is where we're going to use the method of successive approximations. What do you think a good first guess might be? So what would be a good first guess? So what I'll do is I'll call this yn plus 1 of tau. So you give me a yn, and then I'll do this integral, and that will give me a new function, yn plus 1. And I'll now have a sequence of functions. And I can ask, what's going to happen to this sequence of functions? What would be a really good guess for y0 of t? Zero. What do we know about, we know y of 0 is 0. Right? We've normalized things so that we're 0 at 0. When you have a differential equation, you need to give an initial condition. If it's a first order, one initial condition suffices. If it's a second order, two suffice. If it's a third order, 3 would suffice. We've initialized it so that it's 0 at time 0. What's the simplest function you can think of that's consistent with being 0 at 0? 0. I'm not telling you anything about f. We don't know which way f is going. It's as likely to be going up as being going down. So the simplest possible guess is to choose y of 0 to be 0. Plug this in here, do the integral, and now you get y1. Plug it in again, get y2. Plug it in again, get y3. And now you can begin to see where the contraction map stuff is going to be coming into play. If you want, we can do a specific example right now. I can write down, why don't we do that? Let's write down an f, and let's do a specific example. I think I wrote one that's pretty nice. Okay, so example, let's take y prime of t is 2t 1 plus y of t, and y of 0 equals 0. Do you know what the easiest way is to solve a differential equation? Or to solve any math problem? I'd pronounce it divine inspiration, but guess is fine. If y of t equals e to the t squared, minus 1, y prime of t would be 2t e to the t squared, right? And now the minus 1 cancels with that. Perfect. Works. There we go. Not that hard to solve. All right. In general, you are not going to be able to just look at a differential equation and write down the answer. Why do you think I'm able to just look at this and write down the answer? It's not years of experience. Yes? Okay, why do you think it's in my notes? What do you think I started with? I'm sorry? Yeah, I started with y of t and said, well, what do I need if I want y of t to be e to the t squared minus 1? And so I started with the solution and I worked backwards to construct the differential equation, and then I just don't show you the notes of working backwards and just give you the differential equation. Right? That way it's very easy for me to know that here is one that will work. What would my f of ty be? So that's going to just be 2t 1 plus y. Okay? So let's try y0 of t is the function that's identically 0. So we would then get y1 of t is the integral from 0 to t. I'll use x as my dummy variable. I guess we were using tau. I'll keep it as tau. Integral from 0 to tau, 2t 1 plus y0 of t. All right, what does y0 of t equal? 0. So I'm integrating 2t dt from 0 to tau. 2t becomes 2t squared over 2. So this just becomes t squared. Evaluated 0 and tau, so we get tau squared. So we get y1 of tau is tau squared, or if you want, y1 of t is t squared. How should we calculate y2 of tau? That should be the integral from 0 to tau of 2t 1 plus y1 of t, y1 of t dt. So now we integrate from 0 to tau of 2t. And now what's y1? y1 is t squared. So we got 2t plus 2t cubed dt. And when we integrate from 0 to tau, we get, again, 2t becomes t squared, becomes tau squared. The second piece, 2t to the 4th over 4, t to the 4th over 4, so t to the 4th over 2, so we get tau to the 4th over 2. If you look at this, that's beginning to look like the Taylor series expansion of e to the t squared minus 1. How should we view the 2 here? 2 factorial. Do you want to see another term, or are you convinced? One more. Let's do one more term. All right. At this point, there's not really enough data at this point to be truly convincing. And it will actually illustrate a point very nicely. So y3 of tau would be the integral from 0 to tau of 2t 1 plus y2 of t dt. 0 to tau, so we have 2t. y2 of t is going to be t squared plus t squared, t to the 4th over 2 dt. So I have the integral from 0 to tau of, I forgot a 1, of 2t plus 2t cubed plus t to the 5th. It doesn't quite look right. Is that right? Okay, so now when I integrate, this becomes t squared. This one, I'm going to get t to the 4th over 4, so I'm going to get t to the 4th over 2. This one I'll get, okay, it's going to work. I'll get t to the 6th over 6. How should I view 6? 3 factorial. How should I view t to the 4th? Oh, I'm sorry, these are taus, not t's. How should I view t to the 4th? Tau squared squared. So this is tau squared plus tau squared squared over 2 factorial plus tau squared cubed over 3 factorial. So at this point, hopefully, it's becoming really apparent that this is going to look a lot like the e to the t squared minus 1. Before we jump into the general proof, there's a lot we can learn from looking at this example. One of the things that I really like about looking at this example is you can actually see, in this case, that we're getting more and more terms in the expansion of our function. You can see them coming in. Does this look like the stuff we were doing before when we had this telescoping sum with the contraction maps? We wrote xn as x0 plus x1 minus x0 plus x2 minus x1 plus x3 minus x2, and you get these extra little bits that you keep adding. So what you can see here is we're getting all these little extra bits. What should be true about the sizes of these bits? They should be getting smaller. And so this then becomes a question of what space do you work on? This is not a class in differential equations. So I have provided notes for this. They're online. If you really want to see the details, you can look at them there. I'm trying to walk the tightrope between how many of you want to see a lot of theory, how many of you don't want to see theory, how many of you want to see a lot of applications, how many of you don't want to see applications. This is the hopefully half full, not half empty lecture. That there's just enough so that what you want to get out of it, you can get out of it. Okay? There's a lot of technical analysis conditions going on. But the main idea is you can see the series expansion beginning to emerge. And the idea is that when we have these integral equations, and you're given a differential equation, I'm rewriting it as an integral equation that we're trying to solve, it's very similar to our contraction maps. So in order for us to use the contraction map theorem, what do you think we must show? I'm sorry? Okay, so be a little bit more explicit than saying scaling coefficient.
That every time we integrate, or after every iteration, the integral gives us.
It's a little bit more basic than that.
The difference between the subsequent terms is getting smaller.
Right, or a little bit more generally that we have a contraction map. That somehow this integral that we've associated to these differential equations is related to a contraction map. And so this is the part where I was trying to struggle in terms of how much detail to get into. So we have, yn plus 1 of t is the integral from 0 to tau of f of t y yn of t dt. And what we want to do is we want to show that there is a contraction map associated to this. Find the associated contraction map. So if you look at what goes on, we have this operator. It takes a function as input, and it gives you out a new function. This is another reason why I wanted to spend the time talking about differential equations. In our chapter 3 of the book, it talks about after Brouwer's fixed point theorem, there are other types of fixed point theorems you can have where rather than having a fixed point, you end up talking about something being an element of itself. And this is getting used to a different notion. That right now we're so used to functions. You give me an input and I give you a number as an output. Here we have something a little bit more general. Here I give you a function as an input and I have a function as an output. So my space is a little bit different now. So this is no longer a number that comes out. It is for a specific value of t. You give me this should be a tau over here. You give me a fixed value of tau, this is going to be a number. But as I vary tau, I get a function.
So we need some sort of notion of distance between functions?
So we need a sense of a notion of distance between functions. We need a notion of why we're looking at a rigorous way to look at these spaces. So this is not a class that assumes real analysis. So I'm trying to just put enough so that if you've seen real analysis, you have an idea of how to make this rigorous. If you haven't seen real analysis, you hopefully have a sense of why you might want to take a class in real analysis. Why do we need to spend so much time trying to make these things rigorous? Okay? So one thing we could do is we could have two functions, y and w, and I'll say yn, wn, map to yn plus 1, wn plus 1. And just see, are they closer or further apart after we apply? So yn plus 1 of tau minus wn plus 1 of tau, that would be equal to the integral from 0 to 1 of f of t yn of t minus f of t wn of t dt. So if I want to then show that these get closer, I want to somehow show that the distance here is less than the distance between yn and wn. Yes?
What is wn here?
I'm just taking two functions. And so really what yn plus 1 is it's the effect of applying this operator to yn. If you wanted to, I could say I have y, and I could have maybe, I'll call it t of y, my new function. And I have w, and I have t of w. And I want to show that this operator t is a contraction, that t of y minus t of w is less than y minus w. The notation is becoming a bit involved. I can't use the letter f for my map because I've already got f defined over here. So we want to show that things are getting smaller. And this is going to give us a sense of what conditions make f nice. So when you look at this, we have f of t yn of t minus f of t wn of t. I want to somehow get a contraction map. So I want to somehow, I take this and I want to compare to what? So what do I want to compare this to? What do I want to compare yn plus 1 tau minus wn plus 1 tau to? I want to compare it to what?
You want to compare it to one bigger or smaller so you know which direction it's going?
Right, so I want to compare it to yn tau, that's half of it.
Minus wn tau.
Excellent. I want to show somehow that this is smaller than this. So the idea is I want to try to give you a sense of how you would approach these problems, how you would try to figure out what kind of conditions to assume on f, how you would try to figure out how you would get to where you want to go. If I'm trying to show that this is a contraction map, I've got to somehow at the end of the day compare this to this, right? When you look at this, do you see a yn minus wn?
Sure, if f is linear, and if f is bilinear.
So if f is linear, if this is just some multiple of yn and this is some multiple of wn, then that difference is going to be yn minus wn. Forget about the first variable right now. Forget about the t's here. Just look at the second component. What we have here is this quantity over here is just going to be, if you think about it, a Taylor series expansion. Or I could use the mean value theorem. I love the mean value theorem. Mean value theorem is probably my favorite theorem in calculus. If I gave you f of b minus f of a, how would you write that using the mean value theorem? It would be, what would the mean value theorem tell us this equals? Who remembers the mean value theorem? Okay, what does the mean value theorem say? F of b minus f of a
B minus A times F of C.
is f prime of c times b minus a for some c in the interval ab. Another way of looking at it is f of b minus f of a over b minus a is f prime of c. If you look at it this way, it's telling you your average speed is equal to your instantaneous speed at some special point. And that makes sense. Imagine you're always traveling slower than your average speed. So your average speed is 20, and you're always traveling below 20 miles per hour. How the hell is your average speed going to be 20 miles per hour if you're always traveling less than 20 miles per hour? This is not a rigorous mathematical proof. This is literally a hand-waving proof. Right? Similarly, if your speed is always greater than 20 miles per hour, how could your average speed be 20 miles per hour? Either you are always traveling at 20 miles per hour, or at some point you were traveling below, at some point you were traveling above. What theorem is lurking in the background? Intermediate value theorem. So you can get the mean value theorem from looking at the intermediate value theorem and attacking it along these lines. The mean value theorem is a very important technique. This idea of writing it as an average like this is not the most useful way in a lot of problems, because typically we don't have a ratio. We often have f of b minus f of a, some kind of difference like this. And that's why the mean value theorem is so useful. There's another way of rewriting this. Equivalently, this is the same as f of b is f of a plus f prime of c b minus a. What does this look like over here? This one over here? There's a different name than that. It looks like a first-order Taylor series. What prevents it from being a first-order Taylor series? We have a C rather than an A. When we do a Taylor series, we're supposed to expand about 1 point. But a Taylor series is not exact, typically. This is exact. But there's a cost. What's the cost for the exactness? We don't know C. For many things, we don't need to know things exactly. We just need to know that there exists such a C. So here, whenever you see an expression like this, you should be thinking, in what I have over here, I can use the mean value theorem. I can represent this as the derivative of this with respect to the second component, evaluated at some intermediate point. Okay? So this is where we're going to be beginning to get to our contraction map. So what we want to do now is assume the derivative of f with respect to its second component is at most some number m. So we're going to assume the derivative with respect to the second component is bounded. For many functions f, this would be true. The very first example we looked at, f of ty was 2t1 plus y. The derivative with respect to y was just going to be 2t. As long as t doesn't get too large, that's going to be bounded. This is not a huge assumption. We're just assuming that the derivative is bounded. If that's the case, then f of t yn of t minus f of t wn of t, in absolute value, this will be less than or equal to m times yn of t minus wn of t. Right? Any questions about this? I'm just using the fact that the derivative with respect to the second component is bounded, and now I can use the mean value theorem from calculus. And now I'm going to integrate this from 0 to tau. And so now we would get yn plus 1 of tau minus wn plus 1 of tau in absolute value is less than or equal to m times the integral from 0 to tau of yn of t minus wn of t dt. Okay? So we can now begin to see a yn plus 1 minus wn plus 1 over here, and a yn minus a wn over here. Okay? Any questions so far? So I'm going to stop the analysis here. If you want to see the rest of the steps, I've written out clearly. I've posted it online. I'll double check and make sure that the links are working. What I want to do is I want to do enough so you can begin to see the contraction map coming in. You can see it representing itself on both sides. And now you can see that we're going to want some conditions on m. Now, unfortunately, m might be large. The way we can deal with this is now we can say, let's only study our differential equation in a very small interval, so tau can't be too large. And when we start to do something like that, we'll be fine. And we have to define a metric. Maybe we'll look at the maximum difference between these two functions. And then we can replace the maximum distance here will be less than or equal to something times the maximum of the distance here. And I hope at this point you can begin to see now how the contraction is going to come in. This integral should be bounded by like the maximum value of this difference times tau times m. So what do you want to be true about tau times m? So what would you want to be true about tau times m? You would want it to be less than 1. And so what this is going to lead to is this will lead to a solution to differential equations in small intervals about the origin. And depending on how large m is, that will affect how big of a solution you can have. Okay? The bigger m is, the worse things are, and the smaller the interval in which you are guaranteed to have a solution. The smaller m is, well then, the closer these are going to be to each other, and not surprisingly, the larger the region you will get. All right, so this is one of the most important applications of contraction maps. And from this, we associate these integral operators. These integral operators allow us to solve differential equations, and they allow us to do it in several different ways. They allow us to show that a solution exists. They also allow us to show the solution is unique. If you had two different solutions, if you apply this, because it's a contraction map, the difference between them is strictly less than the difference between them. That's impossible. Contraction maps have a unique solution. If you think about things from physical grounds, if you think of your differential equation as modeling something from the real world, should there be a unique solution? At least if you're a classical physicist who has not heard of quantum effects. Should there be a unique solution as to how the planets move about the sun? Yes. We may not know what it is, but there should be a unique solution. Should there be a unique solution to how fluid flows? Yes. Again, if we're assuming everything classically. Whether or not we can write down what that is, that's another story. Okay? And so what's wonderful about this stuff is not only do you get solutions, you get constructive ways of finding them. And again, in life, it is so hard to get a constructive method. Hell, in the proof over here, we use the mean value theorem, which is non-constructive. It says there's some point C. This is one of the things I love about real analysis. Frequently, you don't need to know where the action is happening. You just need to have some control of what's going on. There's some bound m. There's some point C. Now, the more you know about these, the better things are. Okay. So what I want to do now is I want to shift gears and introduce Sperner's lemma. And so we're going to do it on a triangle. Triangles are very nice. I don't want to do this. 1. All right. How well did I draw this? All right, so this, okay, so one of the lines is not so good. All right. So I've taken a triangle and I've divided it up into smaller subtriangles. And I'm going to give the vertices names, 0, 1, and 2. Fortunately, I was a little bit more creative when we were naming our kids. All right? Here are the rules of the games. You have to tell me how to label all the other vertices. And you only have the following constraint. Along the bottom, you can only use 0s and 1s. Along this side, you can only use 1s and 2s. Along this side, you can only use 0s and 2s. Anybody want to tell me a sequence for the bottom? 0, 1, 0, 1, 1. Too long of a wait. Somebody give me something going up on the top. This is your easiest chance to send me an email. Give me a sequence of 1s and 2s. 1, 2,
3.
no! All right, maybe it's not so easy. 2, 2, 2, 2. All right. And let's do the 2 and the 0. All right. Now we're going to fill in. And the claim is there is no way to fill in so that you do not have at some point a triangle where all 3 numbers occur. So I've got 0, 0, 1, 0, 1. What should I put in here? I'm sorry? 0, 1, and 2. Well, I need a choice.
Oh, you choose.
You choose. I'll let you choose. Choose whatever you want. 2. Do you want to come up to the board and just fill them all in? All right. Somebody just give me strings of numbers, or do you want to look at them? We've got 0, 0. What do you want to? And we've got a 0, 2. So what would we put here?
1.
Well, if we put a 1, we have a 1, 2, 0 triangle already.
Well, we already have the 1. Yeah.
Oh, okay. We already have 1, 2, 0. Okay. So we don't want to put a 2 there. The goal is to see if we can fill this in without getting a 0, 1, 2 triangle.
The 1 there.
So we've got to put either a 1 or a 0 here. So if we put a 1 here, we've got a 0 here. What do you want to put here?
Does the 0, 1, 2 triangle at the top count?
No.
Okay.
It's got to be a small. It's got to be a smaller 0, 1, 2 triangle. It will always happen. So you've got 0, 1. What do you want to put here?
0. Zeros everywhere.
All right. So let's see what happens if we put zeros everywhere.
Oh, we hit 1. The 1 that we just did.
So one.
Topmost.
So we unfortunately have a 0, 1, 2 triangle. I'm sorry.
Want to change that 1 to a 2?
Which one?
The one that we put on the camera.
All right, so let's change that to a 2. 0, 1, 2 over here.
Can we change that 1 to a 0?
Yeah.
Or do you want to change this 2 to a 1?
Yeah, better.
That doesn't seem to help.
Now we've got a 0, 1, 2 over there.
I thought those don't
Can you
count.
choose all zeros?
No, no, the big one doesn't count.
Can you choose all zeros
Yeah,
down
she
to
has
the...
to put the little one at the top count.
Right?
Yeah. Couldn't you just, can you choose all zeros?
Well, if we choose all zeros over here, then the 1 and 2 over...
I mean on the side. So one side, make 2 sides all zeros and the other side all 2s. Then there's never going to be a 1 in the triangle.
So put all 0, but
Bottom right
Then
corner.
it's just going to be the corners always.
it's going to be the corner.
So we're allowed, so the corner one counts.
So the small corner counts, yes. I'm saying this big triangle doesn't count. I'm sorry, I might have misinterpreted the question. Small ones over here in the corner count. Big ones don't. So the question is there always going to be some place where you have a 0, 1, 2 triangle? And the way we're going to look at this is almost like directions in which the function is going, and if it's pointing in 3 different directions, as these triangles get smaller and smaller and smaller, the only way that can happen is if you're not pointing anywhere, if it's the 0 vector. And that's going to mean something is not moving. So the idea of something like this is to prove that there is some point that's fixed. You're mapping the triangle to itself. More generally, they're going to talk about these as mapping simplicities to themselves. Rather than doing the 2-dimensional case, what do you think would be a simpler case to do? The 1. So the 1-dimensional case is not that bad to prove. Here's 0, here's 1. Give me any string of zeros and ones. At some point, I will have a subinterval labeled 0, 1. I was going to say there's not enough time to prove it, but there is, because there's at least 10 seconds. So 0, 1, 1, 0, 0, whatever. We know we have a 1 here. We start walking to the left. If we only see 1s, that means we get all the way to here, and now we have 1, 0. If as we walk, we eventually see a 0, great, we've got the 1, 0 triangle. In 1 dimension, it is laughingly simple to prove that you have a 0, 1. It's a little bit more work in 2 dimensions. What does this remind you of? Where have we seen something like this before? Where the proof in 1 dimension was very easy, I was able to do it, and then we haven't done the higher dimension proof yet. We've just mentioned that it exists. Which one? It is similar to that. I'm thinking more the fixed point theorem in 1 dimension. That we could use just the intermediate value theorem. So fixed point theorem in 1 dimension. We map the square, we map the unit interval to itself. If we don't map 0 to 0, and if we don't map 1 to 1, we look at the line. We have to somehow connect at some point. We've got to cross the line. So in 1 dimension, it's very easy to prove a fixed point exists. This is very similar over here, if you think about it, to proving a fixed point exists. And then the question can become, how do you interpret this to mean the same as this? Why are these two so easy? Why is it a little bit harder to do something like this? If we try to put in all zeros over here, we run into some trouble at these corner triangles. So an interesting question would be, how many ways can we fill these things in? Well, we look at how many intersections. Each intersection has 3 possibilities. So if you want to go through all the different combinations, it's going to take you a while. Could you solve this with linear programming? We've got a few minutes left. Can we set up as a linear programming problem trying to assign values in the interior given the boundary so that we do not have a 0, 1, 2 triangle? Sure. One of our variables could be, if the 3 edges, if the 3 vertices of a triangle are different, we count that as a +1. We count that as a great triangle. And then we want to minimize the number of great triangles or distinct triangles or 3-colored triangles in our set, given the assignment. So maybe now instead of doing binary integer programming, we do tertiary integer programming, where our variables here are 0, 1, or 2. And maybe we even allow ourselves to choose the stuff on the boundary with the constraint that down here we can only choose 0s and 1s, here we can only choose 1s and 2s, here we can only choose 0s and 2s. You can set this up as a linear programming problem. It's going to be an integer linear programming problem, so it's going to be hard. It also doesn't have a solution, which is going to make it even harder. There will be no feasible solution. But there's another way of looking at it. What if I just try to minimize the number of triangles that are tricolored? We can do that. And if we try to do that, that's a different linear programming problem. And I will talk about that next time. All right, so again,